Hi, my name is Shania Nicole Muñoz Cardoso, and today I'm going to talk about my experiment 2, design and construction of a microfluidic injection device. In this experiment, we estimated a value for gravity using a Marriott bottle, analyzing its constant emptying flow, measuring the high level of water. For this, we analyzed the velocity at which the water level decreased inside the bottle and used the least squares method to obtain an approximate value for gravity. At the end of this report, we obtain an estimated value for gravity of 1.3427 plus minus 1.1545 meters per second squared. The results obtained were inconclusive as the theoretical value for gravity, 9.81 meters per second squared, doesn't lie within the uncertainty of the measurement. In this experiment, we reference our experiment number 1. In which we explain Marriott's bottle functions. In this report, as we said, we will analyze the average velocities of fusion within Marriott's bottle by measuring the water level height over time. To carry out this work, the height h at which the atmospheric pressure tube is located will be varied. Subsequently, the velocity at which the level of water decreases inside the bottle will be obtained in order to calculate an estimated value for gravity through the experimental procedure. The development of this experiment is valuable since it will allow us to estimate a value using the method of least squares while computing the uncertainties of this experiment. The performance of experiments to check established values is important as it allows us to find out how accurate an experiment can be when it is brought to reality. It can also be used to find the amount of uncertainty said experiment can have, and let us analyze the factors that can be involved. Furthermore, the build-out of this experiment allows us as students to be actively involved in the construction of each part of the report, especially in the calculations and the analysis of the results obtained. As our theoretical framework, we presented the equations used to calculate said value for gravity. We also did an investigation of about microfluidic devices, in which we mentioned the most commonly used microfluidic devices, which are micropipettes. We also mentioned the relationship between Marriott's bottle and this microfluidic injection device. The equipment needed for the development of this experiment consisted in the same equipment needed to make our experiment number 1. In figure 2, we observe a schematic of the bottle where we can observe height h, which remains constant in our experiment, and height h in color green that will be varied. To perform the experiment using a stopwatch, we measured the water level every 2 seconds as the water came out the drain tube. From the start of emptying until the water surface reached height h. This process was repeated 5 times, varying height h to 5 different heights, recording the h versus t data for each value of h. To calculate the h, we use the method of least squares with the measurements of h versus t obtained. By using this method, we will obtain a linear fit that has the form of equation 1. To observe the linear fit clearly, we will elaborate graphs for each experiment using the scientific letter B. The value of the slope of the line will be equal to the constant c of equation 2. Here we can see the tables obtained as results and experimental data. In table 1, we can see the measurements of our device. In table 2, 3, 4, 5, and 6, we see the measurements of T and H for the Marriott's bottle emptying, corresponding to each value of H. And we can also see the graphs for each value of h. To get the velocity, we reported the slopes obtained in the graphs elaborated for each value of h, obtaining the following table. Although 5 measurements were taken, it can be seen that the first measurement is an outlier, since it is quite far from the other data. Therefore, it was not taken into account for the linear adjustment. To obtain a value for C, the following graph was elaborated, and we took the value obtained from the slope. Substituting this value in equation 1, we get that an estimated value for gravity of 1.3427 meters per second squared. We calculated the uncertainties of the values as follows. To calculate the uncertainty of C, we added the percentile uncertainties for T and H. As uncertainty for T, we considered half of the minimum scale, while for H, we considered the sample standard deviation of the data obtained for H in experiment 1. We considered the uncertainty of C to be the same value as the uncertainty for BH, since C represents the slope of the relation between BH and H. For the uncertainty of G, we estimated the percentile uncertainty for both area H and area in, and then we calculated the products of the sum of the uncertainty products of both areas. This value was then multiplied by 2. Finally, the uncertainty obtained for C was added to obtain the uncertainty value for G. As we can see in figures 3 to 7, all graphs H versus T show a linear decrease, which compared to the theoretical framework for experiment 1 is expected behavior of the fluid exiting the Marriott bottle, while the water level is above the lower end of the atmospheric pressure tube. All these graphs present a negative slope. In table 7, we observe that the results for BH obtained are very similar between each other. When calculated BH squared, we see that the value of BH is reduced drastically, obtaining values with a factor of 10 minus 6. When graphing the values obtained, we obtain a slope of minus 7.983 times 10 to the minus 6. This value was substituted in the gravity formula mentioned, obtaining an estimated value for gravity of 1.3427 plus minus 1.1545 meters per second squared. Considering that the theoretical value of gravity is 9.81 meters per second squared, the experimental result is far from this value, since the probable range calculated for the experiment result is from 0.1882 to 2.4972. Consequently, the result obtained differs significantly from the theoretical value, making our results inconclusive. In addition, the uncertainty value obtained is high, as it is of 86%, and therefore the measurement process was not precise at all. This experiment is relevant because we studied one application of Marriott bottle, calculating the uncertainty of the measurements involved and the calculated data. In this experiment, we find out that the uncertainty of the same value can be a very high percentage value and still be far from the theoretical value. During this experiment, it was critical to compute and evaluate the uncertainty in order to provide a better analysis. In further analysis, it remains to investigate how the uncertainty of the development of this experiment can be reduced. On the other hand, it is also important to investigate other ways in which microfluidic devices may have greater efficiency. Thank you.